let us continue with the shortest path problem. So, remember we said that there is a directed graph. Okay. So, E is the set of edges, V is the set of nodes, and then we had weights Cij for each ij belonging to E, and we said that Cij's are greater than or equal to 0 for all ij, non-negative weights. And later on we will consider an algorithm where the Cij's are not necessarily all non-negative. Okay. So, then we formulated the, and I said that Xij will be 1 if arc ij belongs to the path P and 0 otherwise, right. Then we said that the, so the primal problem would be minimize summation Cij Xij. So, this will be right subject to, remember. So, we say okay, we are finding a shortest path from two distinguished nodes. So, let me mention it here, S and T are the distinguished nodes, and we want to find the shortest path from S to T. So, and the shortest path would mean that you add up the weights of the edges or the arcs which make up the path, and then we want to find a path from S to T which has the shortest weight. Okay. So, then the constraints would be, because we want the outcome, the solution here, a feasible solution to this formulation to be a path from S to T, which will require that the summation x s j summation over j has to be equal to 1, because one arc must leave S to begin the path shortest, because we want to find the path from S to T, right. We had gone through this formulation earlier, and then this was Xij j varying j summation over j depending on whether ij belongs to the arc to the edge set or not, my summation xji, right, summation over j, this is 0 when I is not equal to st, right. And then we said that the final this would be summation xjt summation over j is equal to -1. So, because see here for the source node we call it the node from which the path has to be selected, we call it the source node, and T is the destination node. This is also terminology. So, anyway, we want to leave it, we should have at least exactly one arc leaving the node S and exactly one arc reaching node T. And I told you that you can write down the node arc incidence matrix. So, we had gone through all that, right. A is the node arc incidence matrix, right. And we said that for example, if you have so you have A here, and if you have an arc ij here, and you have a node I here and node j, then because ij is leaving node I, so it will have a +1, and it is entering node j, it will have a -1. So, this is the term, all others are zeros. Right. This is the concept of the node arc incidence matrix, and so the constraints can be written like this. So, any intermediate node, if the arc is entering the node, then it must also leave it, and that is why these two sums must always be equal, right. And then now the linear programming formulation, here of course we require the xij's to be integers, but we will show later on discuss why we. So, right now because it is a linear programming formulation, I will just put the constraints that xij's are all non-negative, right. Then we write the dual. So, dual is straightforward, because any column here has only two entries, +1 and -1. So, this will be pi I and this will be pi j, and therefore, when you write the dual constraints, this becomes a transpose of the node arc incidence matrix. So, we are this will be, yes, so he will be pi s and pi t. So, you will be maximizing psi equal to pi s minus pi t subject to, and then you have here yes. So, for example, when you have the node S, if you have the node S here, all this will be plus 1 for any arc of the kind Sj, it will be plus 1 here and minus 1 here, right. So, summation xsj summation over j is 1, right. Then sorry, we are writing the dual, I am sorry, we are writing the dual. So, this is, say for example, here, or do not have to specifically mention this thing corresponding to this, what your dual constraints will look like: pi I minus pi j less than or equal to C I j for all I j arcs belonging to E, right. And since your constraints are equality constraints, therefore, no sign restriction on the dual variables. Okay. So, this is your simple formulation of the dual problem, because any column has only just 2 entries. So, pi I minus pi j. Okay. Now, since we are choosingCij's are all non-negative, so sinceCij's are greater than or equal to 0, we can choose pi I equal to 0 for all I as a starting dual feasible solution, as a starting dual feasible solution, right. You see, the left hand side will be all zeros and these are all non-negative numbers. So, therefore, the constraints are also always satisfied. Now, corresponding to this, choose j as all I j such that pi I minus pi j is equal to C I j. So, that will happen for the starting case, it will happen only when the C I j is 0, because pi I and pi j for the starting dual solution are 0. So, therefore, equality will be satisfied when the right hand side, the C I j number is also 0. Okay. So, this is your set of this thing, and remember the idea is that we want to I am trying to show you good application of the primal dual algorithm. And so, what we will do is we will try to now, so I will call this set, this is the set of admissible arcs. Okay. So, the idea is that if I can find a path from S to T just consisting of the admissible arcs, then I have a feasible solution for the primal, I have a feasible solution for the dual, such that they together satisfy the complementary slackness conditions, and therefore, they both are optimal for the corresponding, for the respective problem, right. So, this is a set of admissible arcs. This explains that only the arcs for which the corresponding dual constraint is satisfied as equality would be admitted for forming a path from S to T. Okay. So, this gives you this thing, and therefore, your restricted primal, what would be your restricted primal problem? You would be wanting to minimize, because I do not know whether I can find a path or not. So, that is the idea. The idea of finding a path from S to T consisting of admissible arcs. So, we will use the artificial variable technique. So, minimize, you can say that something here, did I write something z or something? No, nothing. So, maybe you can minimize phi equal to okay, this will be summation x a I varying from 1 to okay. Now, let me just make one thing clear here. Yes, before I go to that, yes. Yeah. Now, there is a simple modification here. You see that if you add up these constraints, and last time I mentioned it, but I did not show you exactly. So, if you add up these constraints, you see what is happening. An arc S j is a plus sign here, but for node j it will be appearing with minus S j, right, because the arc S j is entering node j. So, therefore, there will be a minus sign here. So, when you add up these constraints, you will actually add up. So, let me say that if you add up the primal constraints except the last one, to obtain summation xjt summation over j equal to 1. This is what I wanted to show. Last time I did not show you exactly. See, because any arc which is appearing as a positive sign in one constraint will be appearing with a minus sign in the other, right, because it is leaving a node S here, then it is entering, and similarly for an arc ij it is leaving node I, but it is entering node j. So, when I write the constraint for node j, it will be with a minus sign, right, the arc xij, and therefore, when you add up you will simply be left with the arcs xjt, because they do not appear anywhere else, right. So, that will be this, and so therefore, the constraint. So, if I multiply this by minus sign, this will be minus. Right. So, this implies that the last constraint will always be satisfied with by a feasible solution for P, right. So, the idea is that I will simply, so therefore, we will ignore this constraint, because as long as I do not have a feasible solution, this will not be satisfied. Only I will obtain a feasible solution once I obtain a path from S to T, that will be a feasible solution here. So, when I am in the process of constructing a shortest path from S to T, then this constraint will not be satisfied, it will only happen at the end. So, then I will simply ignore this, and but I have to maintain complementary slackness conditions. Therefore, we will say that pi t, just keep pi t as 0, this is the idea, right. So, therefore, we will ignore the last constraint, and the by keeping the dual corresponding dual variable always 0, right. Okay. So, now let us write the restricted primal. So, the restricted primal would be minimize summation x a I varying from 1 to what shall I say, or okay, summation x a I not equal to t, otherwise you are summing over all, right. And then you will be saying that summation x s j summation over j plus x a s is equal to 1, and summation x I j summation j minus x j I summation over j is 0, right, where I is not equal to s and t, right. And of course, in the restricted primal, this is for I j belonging to j. What I am saying is that x I j greater than or equal to 0 for this, and x I j is equal to 0 for I j not belonging to j. So, this will be our restricted primal problem. Okay. Only those x I j's I permit to be greater than 0 for I j belonging to j. Okay. Fine. So, now then what would be your restricted dual? Maybe I want to make use of, okay, write it in a prominent place. So, this restricted dual would therefore be maximize. Now, let me write here as pi s bar. So, the restricted dual variables are with the bar, pi s bar, right, because you have 1 there, and subject to pi I bar minus pi j bar less than or equal to 0, and this is for I j belonging to j. Yes, because I only permit those columns here for which the arc is admissible, the corresponding arc is admissible. So, the restricted dual, this becomes this, and of course, we will also maintain that pi bar t is 0. So, that will be maintained, and other pi I bar is greater, less than or equal to 0. No, there will be something else also. Yes, correspond. Yes. Now, no, but I should have. Sorry, there you have to add xai equal to 0, dual variable, right. So, now corresponding to these dual variables, it will be pi r bar less than or equal to 1, right, for all I not equal to t, because pi bar t is 0. Yeah, correspond, because yes, all xi's are there in the objective function, and the columns correspondingly have only one entry for the artificial variables. So, this is pi s bar less than 1, pi bar I less than or equal to 1. So, this is your restricted dual problem. Okay. Now, a very simple way to find, one can find an optimal solution for dr without solving the restricted primal. Okay, this is the beauty of it, and so we will throughout keep up solving the restricted dual problem to construct a feasible path or the shortest path for the primal problem. And this is where you will see how beautifully primal dual algorithm does it for you. Okay, so okay, I will write it here, that is, because I need this dual construction also. Okay, so let us see, one can find an optimal solution for dr without solving the RP. So, the idea is, you see, all dual variable restricted dual variables have to be less than or equal to 1. So, the max value can be only 1. Yes. So, therefore, let us see, try this solution. So, we will start with pi bar s equal to 1 and all other pi bar I equal to 1 if Si is an admissible arc. Okay. So, actually I should write down the rule for constructing the optimal solution for the restricted dual. Start with pi s bar is 1. So, okay, yes, this is an admissible arc, right, and we have already chosen pi bar t as 0, right. So, so therefore, the rule would be pi bar t is 0, and we will say that pi bar I is 0 if node t is, that is a better way to write it, is reachable from node I via admissible arcs. Yeah, okay. See, you have a graph here. So, we have a node S here, we have a node T here. If there is an admissible arc, I am starting with this as 1 and I will start this as 1, right. So, I mean, this, if this arc is there, is an admissible arc, then this also gets a value 1, and so on. And I start from here. So, this is 0. If there is an arc which is admissible and which is reaching t, right, the idea is this. And similarly here, if you have this arc here, okay. So, if these are admissible arcs, then all this will become 0. This is the idea. So, obviously, the thing is that, well, so we will start building it from here. If there is a path from S to T, then through this process, I will ultimately end up putting the value of pi bar s as 1, as 0, right. So, therefore, okay, you might say that we start from here. So, pi bar t is pi bar I is pi bar t is 0 and pi bar I is 0 if node t is reachable from node I via admissible arcs, right. And this we have said, if there are nodes which can be reached from S, then we will give them all values 1. So, these are the two things, and for all other nodes, that means nodes which are which are not reachable from S and from which T is not reachable, both the things. So, for all other nodes, pi bar I is equal to 1. This is the I. Okay. So, you can see that this is a feasible solution for dr. Why is it feasible? Quickly, let us check it. So, here I can show you the feasibility of this. So, what is the possibility? Yes, this is a feasible solution for dr, which means I want to make sure that these constraints are satisfied. So, what do we do it? Now, if I is reachable from S, right, this implies that pi I bar is also 1. Therefore, constraints of the kind pi S bar minus pi I bar is 0, right. So, this is satisfied, right. Then and this will continue for any I j, that means or how do you want to do it? Okay. So, this is this. Now, you take any arc this, you take any arc I j belonging to E, if I is reachable I j, okay, if I is reachable from S and I j belongs to J, right, this would imply that pi I bar equal to 1. And so, pi I bar is 1 and there are and pi bar j is also 1, because if I is reachable from S and I j is an admissible arc, then obviously by our definition, by our construction, pi j bar also takes the value 1, and so this constraint is satisfied, right. And if I j does not, so we can, yeah, I j does not belong to j, right, and j is and T is not, and T is not reachable, T is not reachable from J via admissible arcs. Actually, this should be understood. I do not have to every time say it. Reachable means that I am using only admissible arcs, via admissible arcs, right, and T is not reachable. This would then imply that pi bar j is 1. So, you have that I is reachable from S. So, pi bar I is 1, but I j is not an admissible arc, and also j, you cannot reach T from j via admissible arcs. So, by our construction again pi bar j is 1, right. So, this again implies that pi r bar minus pi bar j is 0, right. Now, the final thing is that if for the arc I j, if T is reachable from I, and there are two cases, I j belongs to j, then we are done. Then this implies that pi bar I is 0 is equal to pi bar j, right, and therefore, this again implies that pi bar I minus pi bar j is 0, right. And if I j does not belong to j, if I j does not belong to j, then what will happen? See, T is reachable from, no, I should have said T is reachable from, sorry, I should have said T is reachable from j. T is reachable from j. So, and if I j is an admissible arc, then T will also be reachable from I, right, because up to j, from j to t I can reach via admissible arcs. I j is also admissible, so I can reach from I to t, and therefore pi bar I will also be 1, and so this will be satisfied. If I j does not belong to j, this implies that pi bar I is 1, right, and pi bar j is 0. So again the constraint is no, hold on. What is the problem? I want pi bar I minus pi bar j to be less than or equal to 0, and we are saying that t. So you have an arc I, you have a this, and you have reachable from t. So this is not admissible. We are saying that if this is admissible, then of course this is also 0, both are 0. But if this is not admissible, then this will be 0, and this is an okay. If it's not an admissible arc, then I should have pi bar I minus pi bar j less than or equal to 0 will not be satisfied. Okay. I'm sorry, this is for only arcs which are admissible. So I should not have added from j via admissible arcs. It's only the constraints are only for the admissible arcs. So let me just forget. Yeah. So this part is not there. This part is not there. Otherwise, you would not have feasible solution. So it's only yes. So that means these constraints are only for admissible arcs, right? So if I is reachable from S, then this takes the value 1, and since I j is admissible, so this also takes a value 1. So this will be satisfied. If t is reachable from j and I j is an admissible arc, then pi I bar is also 0. So then the difference is 0 again. So feasibility is there. So this is a feasible solution, right? So this will not be admissible. Okay. So if now, so I simply want to say, and this I have already said it here, that is yes, I is reachable from S, then pi bar I is 1, and for any I j in E, I am saying that if I is reachable from S and I j belongs to j, then both have value 1, and so the constraint is satisfied, and therefore this implies that pi bar I minus pi bar j is 0, right. This takes place, and if pi bar j yeah, and so this also goes out. Yeah. And if t is reachable from j and I j is an admissible arc, then both have value 0, and so this happens. And if yes, so the third case is that I j belongs to j, and I is not reachable. Yeah, this should have been, is not reachable from S, and t is not reachable from j. Okay. So that means it's simply an arc I j, and there's no path connecting it to S, or there's no path connecting t to j, from j to t. So then in that case, by our construction, we said that here, where was it? So for all of the nodes, it should be, sorry, it should be 1. For all of the nodes, it is 1, right. So therefore again the two values will be the same. In this case, this is admissible. So therefore this will imply that pi bar I is 1 is equal to pi bar j. Yeah, the construction has to be sort of very clear in the mind. So this is pi bar, this is 0, and therefore again the constraint will be satisfied for the admissible arc. So this is a feasible solution, and since the maximum value for this cannot be more than 1, and I have already, and so this feasible solution has that maximum value, therefore it is optimal. So I did not have to use the optimality criteria or anything. It is just by observation we are saying we have found an feasible solution to the restricted dual, and the maximum value is attained, therefore it must be the optimal solution. right. So, this is how things become simple. Why? Because the structure of the problem, you see the constraint set has a very simple structure here. The dual problem, the dual constraints are very very straightforward. So, we can by observation look at obtain a solution for the restricted dual, right. Fine. So, as long as max pi bar s is uh, positive, which is equal to 1, that means your restricted dual, restricted primal does not have the 0 value. Remember, all the artificial variables have to leave the restricted primal in the feasible solution. So, yeah, so what we were saying is that because we are exploiting the structure of the problem here, and since the value here is not 0, therefore, I do not have a path from S to T, which is my which is the idea behind this whole exercise. Okay. So, now I need to therefore modify the dual solution, because the current dual solution is not yielding a primal feasible solution. That means, the admissible arcs are not enough to give me a path from S to T, right. So, we will try to get some more arcs which can become admissible. That means, I have to modify the dual solution, and remember our this thing was yes. So, this once we know this is done, I can now. So, we need to modify modify the dual solution, and here again you will have to recall. So, that and our method was to do it pi plus theta pi bar, and we will choose theta in such a way that this solution is dual feasible, right. And by pi bar I already showed you the construction for the restricted dual. So, this is this, where of course, we have to first compute theta. So, you see here again in pi bar what is happening. So, now we will be adding an arc which is not in J. Remember, I need to expand my set J. So, you can see from here that an admissible arc, okay, you want this to be less than or equal to Cij. I am just trying to think what is the best way to lead you to to obtaining the value of theta. So, anyway, let us see, this is this, right. Now, if pi bar, so here again, yeah, this sorry, this is less than or equal to C, right. So, a typical constraint, that means for ij belonging to E, the typical constraint will be pi I minus pi j plus theta pi I bar minus pi j bar less than or equal to Cij. This is what, if I modify my dual solution and this is my new dual solution, then this is what I have, right. Now, as long as pi I bar minus pi j bar is less than or equal to 0, I do not have to worry, because, and of course, here this is an understanding that theta is greater than 0 in fact, because you want to modify. So, theta has to be chosen positive. So, if theta is positive and this thing is less than or equal to 0, then I do not have to worry about it, right. And this will happen when, see, corresponding to my restricted dual solution, if the see, some pi bar i's have value 1, some pi bar i's have value 0. So, if, when will this be negative or less than or equal to 0? Either of course, the two values are the same. In that case, the arc has to be admissible. Remember, the way I constructed, any admissible arc will allow you to fix the same values for the restricted dual variables, and therefore, this will be satisfied as equality. So, when this is 0 and this is 1, that means your so this will be this case less than or equal to 0. We do not want that, because that is not a problem for us. The constraint will be satisfied, right. As long as this is 0, no need to worry, right. Okay, I am just writing our no need to worry. Any value of theta will satisfy the dual constraint, right. So, need to compute theta when pi I bar minus pi j bar is greater than 0. And when will that happen? When pi bar I is 1 and this is 0. That means you have a path from S to I that either this has a value 1 because there is a path from S to I, and then you have pi bar j, node j here, and there is a path from here to T. This is one situation. So, this will have a value 1 and this will have a value 0. So, one of them has to be, because both 1 again will not give me 0, will give me 0. So, I need this to be 1 and this. So, either node I is not reachable from S, then also we said that the value would be 1, right, and or it is reachable. In that case the value is 1 here and this is 0, because, so you see now I will, well, once I say that you do this, and then we will need to compute, that means I need to compute the value of theta from such, for such arcs, because once this is positive, then depending on the value of theta, this may violate this constraint. So, therefore, I need to fix the value of theta such that it does not violate. So, then what do you get? You get that theta should be less than or equal to Cij minus pi I minus pi j divided by pi I bar minus pi j bar, right. And so, we choose theta to be minimum, where of course pi I bar minus pi j bar is greater than 0. Right. So, it will be minimum of Cij minus pi I minus pi j divided by pi I bar minus pi j bar, and pi I bar minus pi j bar is greater than 0. So, among all such things, that means you will certainly be adding an arc of this kind, where j from j there is a path to T, and now you, by adding this arc, and there may be many others here. So, you will be choosing the minimum of all these for this ratio. So, you will have at least one arc which was not there in j, and why? Because your pi I bar minus pi j bar is positive. See, for admissible arcs this would always be equal, as we saw by our construction, right. So, this is what is it. So, you choose your theta to be such, then if this minimum occurs for, let us say, what do you want to say here, something like, okay, take some arc Lk or something. So, this was our theta will be computed this way. Now, for whichever arc, let us say this is attained for Clk minus pi L minus pi k, and actually this is the value, because this is equal to 1. Whenever this number is positive, it has to be 1, because we are giving the values to pi bar I and pi bar j as 0 or 1, right. So, whenever this is positive, this has to 1. So, actually your theta is nothing but this number, right, and for this number you see your when you do this pi L minus pi k plus theta times pi L bar minus pi k bar, right, this will be equal to Clk. That's because of the definition, right. This is theta, so you multiply this by this is 1. So, when you have updated your solution this way, this becomes equal to, see, from the definition, because this is 1. So, just see from here, this, when you bring it to this side, this thing, this becomes Clk. So, this is the equation. So, therefore, you have one more, and so this implies that Lk has been added to J. And we will also this can be an exercise, or we will discuss it in the next lecture, that if an Ij belongs to J, then Ij will always continue in J, right. That means, once an admissible arc, it will always remain an admissible arc, and I will continue with this later, but let me now just show you how the algorithm progresses. Okay, so the idea would be that I update my dual solution with pi plus the updated dual solution is pi plus theta pi bar, and then again I have a new set j, an extended set j. I will again try to find a path from S to T, and this searching for the path is very straightforward because you will be at the dual restricted, you will be able to get a solution, and if you can label in the sense if you can put pi s bar also as 0, then you are done, right. So, we will continue with this algorithm till we arrive at a path from S to T. So, the aspects that okay, how much effort will it be required, and that we will always find an optimal solution to the shortest path problem, all those things I will discuss in the next lecture, but here let me just show you the iterations of the algorithm, so that you get a feel for it, and then we can understand the proof better once you know how the algorithm is progressing. So, here you see the numbers on the edges, on the arcs, give you the weight, theCij's, right, they are all non-negative. So, your dual constraints, if you want to write them somewhere here, except that I need more, okay, yeah, I can I think remove this also. So, if you write, I can straight away write the dual solution, right, I do not need to write the primal, because for each arc this will be maximized, yeah, and so this is simply pi s, oh sorry, yeah, maximize pi s subject to pi s minus pi 1, right, less than or equal to 2, and these are the kind of equations you will write. Pi s minus pi 2 is less than or equal to 1, pi 1 minus pi 3 less than or equal to 3, then pi 1 minus pi 2 is less than or equal to 3 for the arc 1 3, right. Then you have 2 to 3. So, pi 2 minus pi 3 is less than or equal to 5, pi 2 minus pi 4 less than or equal to 1, yes, okay. Then you have 3 to t. So, pi 3 minus pi t less than or equal to 2, less than 2. Then from 3 you have nothing going in, and from 4 you have pi 4 minus pi 3 less than or equal to 2, and pi 4 minus pi t less than or equal to t, right. And we are saying that, so you could say that why am I writing pi t's, but it does not matter, pi t is 0 and all other pi i's are can take any value. So, this is your dual solution, right. So, we can choose the starting dual solution as all zeros. I am not writing pi t 0 because that is understood, no point carrying it all the time, because all these things are non-negative. So, when I put all pi 0, I have a feasible solution, right. And so, the starting your j is empty, there are no constraints, no dual constraint satisfied as equality, because all these numbers are positive. Oh, pi t, what did I write here? This is 4, okay, fine. So, j is empty, and therefore, you simply now need to, and so what would be your this thing, yeah. So, remember since j is empty, there are no admissible arcs. So, I will write the values of the restricted dual here. So, this is only 0 and all others are 1, 1, 1 and 1. Is it okay? Or if you want, you starting to the solution, and then so you will have to write pi bar as 1 1 1 1. This is it. So, you need to compute theta, and remember, to compute theta we have to go for arcs for which this is equal to 1, and since this is 0, you see for this arc and for this arc the value is 1. Pi 3 minus pi 3 bar minus pi t bar is 1, and pi 4 bar minus pi t bar is 1, right. So, yes, and what is your what are your Cij? Yeah, the thing one has to streamline here is you understand where you get the quantities. So, this is right now, since all pi i's are zeros, I simply have theCij's. So, I have to, that means take theta theta will be simply minimum of your C3t and C4t, and I will try to show you how to get the values as you proceed. So, this is C3t, C4t, right, which is minimum 3t is 2 and this is 4. So, this is 2. So, your theta is 2, and therefore, your new dual solution which is pi plus theta pi bar. So, twice this you have to add here. So, this becomes 2, 2, 2, 2, 2. This is your new dual solution. Okay. And since the minima occurred for arc 3t, you see your J now contains arc 3t. Yes, the J contains arc, so this becomes admissible. So, so therefore, the restricted dual solution is immediately available because this is 0 and this is the only arc which is admissible arc. So, this becomes 0. So, let me write it for you. So, this was your new dual solution, and your pi bar now becomes 1, 1, 1, 1 and 0. Well, let us see, it will be this way because node 3 comes first, 0, 1. This is your new restricted dual solution. So, this remains as 1 pi bar s, the maximum value, because I do not have any other admissible arcs. So, you can see actually see that this is how you are constructing the path. You have chosen arc 3t as admissible arc, and you are able to connect 3 to t, right. Okay. Now, you might say that so here either you can keep writing the dual solution here. Well, okay, in the next lecture, right now I want to show you the iterations, and then we will come back to streamlining the presentation so that you can get the quantities as you want. Fine. So, therefore, need to compute theta. So, compute theta again, and for theta again you see because this number is 0. Okay. So, maybe you can, this number is 0. So, now you have what are the possible candidates? This is 1, right, pi bar, remember pi bar 1 minus pi bar 3 is 1, then pi bar 2 minus pi bar 3 is 1, because this is 1, that is 0, and pi bar 4 minus. So, the theta would be minimum of, okay, so let us write it down quickly. This will be C13, right, C13 minus pi 1 plus pi 3, this is 1. Then it will be minimum of C23 minus pi 2 plus pi 3, and finally, this will be C43 minus pi 4 plus pi 3. This is how we compute, right. So, this will, you have to choose minimum of, now C13 the number is given to you here. So, 3 minus, and we have the dual solution here, right. So, 1 3. So, remember 1 2 3 4, well, S 1 2 3 4. So, what is this value here? So, this is again it is coming out to be minimum of the, because these numbers are the same, pi 1 and pi 3. So, therefore, this simply be C13 is 3, C23 is 5, and C43 is 2. Okay. Is it fine? Because all these numbers are the same, the dual solution is the same. So, therefore, they do not contribute to your computing the minima, it is only theCij's which are required. So, this is 2. So, your theta is 2, and therefore, your new dual solution pi would be theta, twice this you add here, right. So, that will become yes, we have to be careful, 4 4 S 1 2 and 3 1, this is 0. So, that remains 2, right, and that becomes 4. Is it okay? Yeah, twice this you have to add here. So, these 3 become 4, this remains 2, and this is 4. So, this is your new dual solution, right. and you have chosen the arc, 4 3. So, therefore, you see this is you step by step you are constructing your shortest path. Okay. And so, once you have this, then I need to the j becomes that, and you still have the value of pi bar s as 1 for the restricted dual. So, I need to update my dual solution further, and that means that I need to, and so what would be your restricted dual solution now, right. So, maybe let me update it here only, or you want me to write it here. Okay, yeah, I can do it here. So, the restricted dual in that case, once you know your j, so what is my j? Remember, you have to keep updating your j. So, your j I will write here, j now consists of 3t and 4 3. This consists of this, right? Yeah. So, my what is my restricted dual solution? Pi bar. So, this will also become 0, and all others remain 1, because nothing is no admissible arcs here. So, this all remains 1, right. See, want to give you the correct form of set J, which is the collection of all the arcs for which the dual constraints are satisfied as equality. So, arc 4 comma t was left out, but if you look at the dual variables, then you can immediately check that the dual constraint for arc 4 comma t is also satisfied as equality. Therefore, arc for 4 comma t should figure in the set J. So, once you have your pi bar, well, if you want me to write it here, this is 1 1 1, then 0 0 0. This is your restricted dual solution, right, and we need to compute the theta. So, what will be theta now? Yeah, I am writing all the steps so that it becomes very clear, and then we will streamline the algorithm. So, minimization, now this is all 0. So, here you see this will be, you can start from there, this will be 1 3. So, write C 1 3 minus pi 1 plus pi 3, right. Then it will be 2 3 again. So, C 2 3 minus pi 2 plus pi 3, right, and then you have this 2 4. So, this will be C 2 4 minus pi 2 plus pi 4. I think that is it, because these two are zeros. So, you have this, this and this, these three. Yeah. So, let us quickly, because I have my dual solution here. Yes. So, write down the values. Minimum C 1 3, C 1 3 is 3 minus pi 1 is 4, and pi 3 is how much? So, this is, yeah, I am just writing the values and then we can check. So, then C 2 3 is 5 minus 2, which is again 4 plus 2, because C 3 pi 3 is 2, and then you have 2 4. So, 2 4 is 1 minus this is 4, and what do you have for this? Plus 4. So, therefore, this is equal to 1, and this corresponds to what arc? 2 4. This corresponds to arc 2 4. So, the new value, that means theta is 1, and therefore, you have to update your dual solution. And yes, in the meantime, I should have asked you to please verify that your what you have is always a dual solution. So, do this while you are going through this example, you do this fine quickly. So, let us just compute our dual solution, dual feasible solution, and this would be, yes. So, theta is 1. So, 1 times you have to add this to this. So, what will it be? Your nu is 5 5 5, right, and then it is 2 4. Then somebody correct me here, 1 2 3 4 5. So, why am I writing this here? Yes, this and 2 and 4. So, this is your new dual solution, right, and you see that this becomes 2 4 gets added, and your j gets updated to j gets updated. So, this is the new arc that you have added here. So, now you have 2 4 4 3 3 t, right? These are the arcs that you, this is this. And so the new restricted dual solution I am showing here will be, this is 0. Yes, and you see that now immediately you can, all these are 0. So therefore you have 2 arcs, 1 2 and okay, 1 2 and S2, and that is it. So now when you choose your theta, that will be for arcs S2 and 1 2, right? And you can immediately see that here this will be the arc. Fine, I will leave that to you. You sit down and work it out that your theta will occur for this, the minimum value, right? And therefore you now have a shortest path. So finally when you do this, then because this becomes admissible, so your new restricted dual solution, this will be 0 and you are done, because your pi bar s is 0, you have obtained an optimal solution to the restricted primal, and so you have now an optimal shortest path from S to T, which consists of this, well, okay, how are you going? S to 2, 2 to 4, 4 to 3 and 3 to T, and the total length is would be here, 1 get added, so I think it will be 6, 1 2 4 and 6. So there are very interesting interpretations which I want to further show you, that the dual variables at each iteration for the for certain nodes will always give you the distance of the node to the node T, the shortest distance. So interesting application interpretation of the dual variable. I will streamline the algorithm, but you now get a feeling as to at each iteration the restricted primal or the restricted dual is nothing but building up a path from a node to the node T, and that path is the shortest path. So we will look at this, I will revisit this example and show you the streamline the algorithm.